What up, chemistry people? Today we are going to carry on with our oxidation and reduction stuff, and what we're going to start with today is how do we even know if something is a redox reaction? So what we started with is, well, what is oxidation and what is reduction? And what we learned to do is figure out what the oxidation numbers of stuff was, because you got to know the oxidation number to see if it's changing, and if it's changing, then you know you got an oxidation reaction. So why do you want to know that? To see if your reaction can be made into a battery. You got to know if your reaction, one, is a redox reaction, and if it is, can you make it into a battery? Like, that's like the whole main point of this stuff, is getting down to seeing how we make a battery work. So, without further ado, let's just dig right into it, because today we're going to talk about this, a redox reaction. Ooh, whoa. Sorry, there you go. We're going to talk about redox reactions. That guy right there. One of the things that I want us to look at when we're doing this is I need us to, oh, forget that. I want us to make sure that you guys are dialing, not all these are going to be perfect. I want you guys to remember that you have to have like both oxidation and reduction all at the same time. Right? You can't have one without the other. You can't have the other without the one. That's why we say redox. And there's a reason for this, okay? Because wherever one goes this way, the other is going to go that way. They kind of complement each other, okay? So remember what redox even means here, guys, right? Redox, there you go. Look, is oxidation and reduction. You can't have one without the other. They are totally like interwoven, you know what I mean? So here's the deal. For it to be considered a redox reaction, there has to be a change in the oxidation number, right? Because if the oxidation number tells us how many electrons it has gained or lost, well, it has to gain or lose. It's like accounting for electrons, so it has to change. It's like like the oxidation number is like a bank account for your electrons. You got to either make deposit or withdraw in order for it to be a redox, right? Which is why we spend all that time trying to figure out what the oxidation numbers are, because we are going to be looking at all of them. Yeah, by the end of this chapter, you're going to be doing oxidation numbers like this, right? So, the change in oxidation number is how we know there is that electrons have been transferred, and the clutch thing here, my friends, is change. It has to change, right? Because that means that electrons went from one place to the other. All right, so let's have a couple examples here. Is this a redox reaction? So what I'm going to do is, one, I'm going to look at all the oxidation numbers, both in the beginning and the end, and then we're going to compare, see if there's any changes. So let's dig into it. Here, oh, hey, this is kind of nice. Do you see how this is an NO3 here? Right? It is a polyatomic ion. Also, on this side, I have another NO3, right? No other evidence of nitrogens or oxygens in there. So this NO3, which is a -1, because I looked up on the reference table, it's still going to be a -1 over here. And you don't have to worry about it, right? Because it's a polyatomic ion. It's like not changing. So definitely no oxidation number changes there. And this silver, if it's to an NO3, must be a +1. That's easy. All right, so let's go over here. Potassium, group 1, definitely has to be a +1. And this is chlorine. Chlorine's on the negative side, right? It's like over there on the right. So it has to be in the negatives, and it has to be -1 to cancel out like this guy. Yeah? All right, so let's move over here. Here we have silver and chlorine. Not really sure what that was, but silver is also, I look it up. Silver is a +1, it's a +1, it's what silver is, and chlorine is going to be a -1, because it's on the negative side. That's all that chlorine can be. And this guy right here, potassium, it's group 1, so it will be +1. So what we then need to do is we need to start comparing. Silver, it started as a +1, it ended as a +1. No change. All right, NO3 started as a -1, ends as a -1. No change. Potassium starts as a +1 over here, +1 over there. No change. Chlorine -1. Chlorine -1. Guys, is there any change here at all? No, not a redox reaction. This is not a redox reaction. No electrons have been transferred. It is a chemical reaction. There is a chemical change, right? We have this really wonderful like precipitate thing going on right here, right? Aqueous, aqueous, solid, aqueous. It's a precipitate reaction, but definitely not a redox reaction. No electricity happening here. Let's move on. Now here's one. Now let's check these out. This one, let's stay gold. Zinc, not in a compound, it's by itself, therefore it must be 0. Hydrogen, it's group 1. It's also hydrogen, it's weird, so it's in the plus position, so it's going to be +1. And chlorine, well, you know, we all know chlorine, it's on the negative side, it's going to be -1. It has to be to cancel out that one. Zinc, if I look at the periodic table of the elements, zinc will be +2. And chlorine, it's on the negative side. If you look at the periodic table of the elements, chlorine has one negative option, and that is -1. And then here is hydrogen all by itself, uncombined, not just it's in pure elemental form, so this is going to be 0. Dig? All right. Oh, wait, let's double check. 0, +1, -1, that cancels out. This is a +2, but that's a -1. Oh, wait. There's 2 of them, so I'll have a total of -2 in all. Perfect. All right, let's see what we got here. So zinc before is at a 0. Hydrogen is a +1, and chlorine is a -1. That's what it is before, and after it looks like zinc turns into a +2. Looks like hydrogen goes to a 0. And chlorine, yep, chlorine's staying at a steady -1. Now, is this a redox reaction? You bet. Oh man, this is gonna get like sparkle space. Ooh, I don't know what that's going on. Yeah, right there, buddy. Yes, yes, yes. Redox reaction. Look, there's a change here, and there's a change here. Boom, and look. I want you to clue you in on a secret shortcut that I'm not supposed to tell you guys, because they're like, oh, it's part, they're supposed to just, they're not supposed to have, I don't care about the Regents people anymore, do you? I sure don't. So look, you see how this zinc is a 0? See how it's in like pure elemental form? There, that's much better. You see how this zinc is at a 0, and then on this side it's in a compound? Look, element, compound. Guaranteed. Every single time. If you see an element on one side and a compound on the other, guaranteed redox reaction. Same thing, except different over here with the hydrogen. See, there you got hydrogen all by itself, uncombined, and over here on the other side of the chemical reaction, it's in a compound. Guaranteed. Guaranteed if you have something in a compound on one side, element on the other, you don't even have to go any further. And this is something I need you to be able to do, is to look at a chemical reaction and recognize whether it's a redox reaction or not. And how do you do that? Well, you look at all the oxidation numbers, and if there's no change, no redox. You look at all the oxidation numbers, if there is a change, then it is a redox reaction. Bing, bang, boom. That's simple, you know what I'm saying? Easy peasy, lemon squeezy. So, that being said, when there is a redox reaction and we know that there's a redox reaction, one of the things we need to be able to do is tell who is doing the oxidizing, who is doing the reducing, who's doing what here. Well, that's where these things come in. Oxidizing and reducing agents. Here is what that means. Here's our, oh, that's a little too far. Here we go. So here's our situation. Here is potassium all by itself. It's 0. Here's bromine all by itself. And then here we get a +1 and a -1, right? So, great. Potassium goes from 0 to +1. Bromine goes from 0 to -1. I see that this right here, the charge is lowering. The charge is being reduced. So if that one's being reduced, the other one has to be oxidized. You guys picking up on that yet? I like this thing. I really, really hope so. But anyway, all right, so here's the deal. Here's how we determine who is, so this is like, these are our two things, our oxidizing agent and our reducing agent, right? Here's how we're going to identify them. You kind of walk through it like this. Potassium was oxidized, right? See, it's losing electrons, Leo. Gaining electrons, Ger. Potassium, and remember, there's only going to be two things here. One thing is going to be oxidized, one thing is going to be reduced. You got it? So these guys are going to be the agents because this is what it is before the reaction, and this is like where it's all after. So potassium was oxidized, specifically potassium 0. So potassium 0 was oxidized by bromine 0. Does that make sense? Because who could have oxidized? Who took the electrons, right? So what's happening here is if potassium is being oxidized, electrons are leaving potassium and going into bromine. Well, you know, potassium lost them. It was oxidized. By who? By bromine. Bromine did the oxidizing. So the substance that oxidizes something else is called the oxidizing agent. Got that? That's a vocab word. There might be a vocab quiz. Right? You get it? Do you see how that works? And same thing for the reducing agent. You go through the exact same line of questioning. Bromine was reduced by who? Well, bromine 0. Bromine 0 was reduced by potassium. Right? So that means that this, our potassium 0, is going to be our reducing agent because the potassium reduced the bromine. Just like over here, the bromine is the oxidizing agent because it did the oxidizing. Does that make sense? Like an agent of good is someone who goes around and does good. An agent of evil runs around doing evilness. Same thing with oxidizing and like reducing. Does that make sense? Okay, so this is one way you can tell right here, like by using oxidation numbers and like looking at the equation and asking yourself, who got oxidized? Who by like, all right, such and such was oxidized. Who did that? Who did the oxidizing? Well, whoever was reduced. Oh, let me go like this. Whoever is reduced is always the oxidizing agent. And whoever is oxidized is always the reducing agent. Agent red. You guys get what I'm saying? Because it's kind of opposite. The potassium has to get oxidized or in order to reduce this thing. And this thing has to get reduced in order to oxidize that thing. It's kind of like opposites, right? But if we're not sure, how do we know who will be a reducing agent and who will be an oxidizing agent? Well, here, right here, table J. So this is how we can predict, all right? So this is how we identify this whole mess that you have right here with my digital pen thing. But as chemists and scientists, we usually want to make predictions. Like we want to know what's going to happen before we blow stuff up. So we will use table J. Here's how table J works. First, the first two pillars of knowledge in this. There are 5 pillars of knowledge in this chapter. There are Leo, says Gur. Here is the third one. We got it? This is the third pillar of knowledge right here. Electrons roll. Downhill. Well, on table J anyway. So here's the deal. Table J tells us where electrons are going. They are like, the higher the, let's just go through it. The higher a metal is on table J, the more likely it is to lose electrons. Does that make sense? Great. So the higher metal is on table J, the more likely it is to be oxidized, and therefore it's more likely it's going to be a better and stronger reducing agent, right? So on table J, electrons roll downhill. You got it? Electrons will go from the metals higher up on table J to the metals lower on table J. So when we try to set up our battery, right, we're going to have 2 metals, and the metal that's higher on table J will lose the electrons, and the metal that's lower on table J is the one who's going to gain the electrons. So the electrons are going to go from that metal higher on table J to the metal lower on table J. What that means is if it's higher on table J, it's losing electrons. It's being oxidized, and therefore it is a reducing agent because it's like smashing those electrons down on the ones that are below it, right? So the ones below, like those are the ones that are like taking all the electrons. Those are the ones that are being reduced. And like vice versa, the low ones are stronger oxidizing agents because they're more able to rip electrons off of the higher metals. Oh, over there on table J. Got it. Sweet. Yeah, this one's not a very complicated one today because that's it. We're done. So here's the thing. Right over there. Right over there. That is your homework assignment right down there. Right? So what I want to do is I think I want to try going over one or two of these with you. Analyzing oxidation and reduction reactions. So here it is. It says, for the following examples, determine the oxidation states for the elements on both sides and blah, 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 blah. Then determine which element was oxidized and which was reduced. That is the core to everything. Because anything over here that is oxidized, anything that's oxidized is the reducing agent. Anything that gets reduced is the oxidizing agent. You guys picking up what I'm putting down? All right. So let's go over where I can like use my pens and stuff because that's what I like to do so I can draw and stuff. Let's do purple. All right. So here's how we do. Step one, we're going to find all the oxidation numbers. And here's there's a little trick I have because my eyes don't work very well. So here's how I do. Go through the oxidation numbers. Magnesium, it's all by itself. Therefore, its oxidation number is 0. Oxygen is all by itself. Therefore, its oxidation number is 0. Now remember, this is a very simple one. We're just starting. Over here, we have magnesium. I look up over there on the periodic table of the elements, and sure enough, magnesium is a +2 because it's in a compound. Then I'm going to look up again. Yep. -2. Delightful. So then what I do is I connect the ones that have changed. And granted, there's only 2 here, so it's not really necessary for this one, but it's more like just to like learn the technique, you know what I'm saying? So here's the deal. Then I like to come over here to the side. I'm just going to start with magnesium. It goes magnesium 0 turned into magnesium. What did it turn into? It turned into magnesium 2+. So is that gaining or losing electrons? Well, you're right. That's going to be losing electrons. Oxidation. So now remember, you got to like, these are the only ones that are oxidized or reduced. The stuff over here is when it's all done. So that is what happened there. And so for oxygen, it went from oxygen 0, it turned into an oxygen with a 2- charge. That is obviously gaining electrons. Leo says, grr, gaining electrons is reduction. Yeah? Does that make sense? Let's try one more. This time I'm going to pop my face right over here. Okay, so now there are a few more. Actually, no, forget it, man. Let's since we're here, let's go down here. Let's try this one. Let's try number 4 because this one looks really, really difficult. All right, so I'm going to go back to purple for my numbers. And here's the thing, like the reason why we're doing this is because as crazy as this thing looks, I mean, there's a lot going on there. There's one thing that's going to be oxidized. There's one thing that's going to be reduced. Full stop. This is as far as we're going in this class. We don't need to get any more complicated. So there's only going to be 2 things that are changing. Let's go figure them. All right, potassium, group 1. Oh, chromium. I don't know what that is. Okay, so I'm going to go like this. Well, potassium is a +1. Oxygen is a -2. Going to have to figure this out here. So let's go to the red. Okay, there are 2 potassiums. There are 2 chromiums. There are 7 oxygen. You see why I had you guys do this homework the other day? Potassium is in group 1, so it's a +1. This is my X, and oxygen is a -2. And by the time you're done this worksheet, I'm also hoping that you can do this like right in your head really quick. So this is 2 plus 2x minus 14. X equals, let's see here. It's 14 minus 2, that's 12, that's 6. Sweet. Okay. Hydrogen, it's always +1. Oxygen is always -2. This is something, sulfur. Oh yeah, see how it's all by itself? Goose egg. All right, over here, potassium. Potassium is a group 1, so it's always going to be a +1. This is a polyatomic ion, the hydroxide ion, so you know that's a -1 in all, but I'm going to have to break it down. Like, I know that oxygen is always a -2 because it's not H2O2. Hydrogen's going to be a +1. It's a little weird, but it's because it's in that polyatomic ion, that OH, hydroxide polyatomic ion. You should know this from the last chapter. That's why we did it last chapter. Now let's come over here to oh boy, don't know chromium. I know that oxygen is always -2 unless it's an element or in a hydrogen peroxide. So we're going to have to do some more figuring here, aren't we? All right, so you all right, bud? Yeah. All right, so we got 2 chromiums, 3 oxygens. Chromium is an X, oxygen's a -2. We get 2x minus 6 equals 0. X equals 3. So here I'm going to put... Yeah. All right, now let's come over here. Sulfur. Oh, I don't really know what that is. Periodic table ain't helping me. All right, so I'm not scared, man. It doesn't matter. There's 1 sulfur. There are 2 oxygens. Sulfur is an X. Oxygen is a -2. X minus 4 equals 0. This must be a +4. All right, so what do I need to do next here? First, I'm going to clean this stuff up here. Okay, now what I do is I'm just going to go through and I'm going to look for stuff that changed, right? Potassium +1, potassium +1. Chromium +6, chromium +3. Oh, there's a change. So chromium went from +6 to +3. We went from +6, and then over here on the right-hand side, it turned to a +3. See, what I'm doing is I'm extracting it so I don't have to look at all the other garbage around it. You know what I mean? Because my eyes do not work with all of the noise going on down there. So this is what I do. First, I draw a line to connect it to, like change, right? This looks like chromium 6 turned to chromium 3, so I draw a line to connect them. And then I just write it out, chromium 6 turned to chromium 3. So let's keep on going here, shall we? All right, oxygen is an O2. All the oxygens are, oh, I forgot to write that down. Okay, hydrogen +1, hydrogen +1. Oxygen -2, oxygen -2, sulfur 0. So, oh, here it is. Yep. Sulfur 0 turned into sulfur 4+. So sulfur 0 turned into sulfur +4, 4+, whatever. Don't judge me. I won't judge you. So let's look at this. This looks like the charge is going down. So I'm going to call this reduced. GER, gaining electrons is reduction. So it makes sense that this would be reduction because gaining electrons means negative. So the charge has to go down. Charge is going down. We'll call it reduced. And this is going from 0 to a 4. Definitely oxidation because it's losing electrons. It's getting rid of that negative charge. So of course it's going to be more positive. So that happened. You got it? All right. So oxidized is S0. And reduced is my chromium. And this is why it's really important to write down whether it's 6+. Because if you just say chromium, well, dude, look, we got right here, we got chromium +6, and over here we got chromium +3. Man, they're both chromium. But they are totally different. Like wildly, completely, and totally different. So that's why we got to include the charge so we know exactly what we're talking about. You dig what I'm saying? It's like, yeah. Are we good on that? So that's how we're going to do 1, 2, 3, 4, 5, 6, like the whole front and back. Like there's 2 pages of this. And the reason why I want you to do it is because I need you to get like second hand at doing this oxidation number. It'll save you a ton of time. And then I want you to see that even though you may have a very big complicated reaction when it comes to the redox, for us starting out, it's simply 1, 2 things. It's just this simple right there. You dig? You dug? That's awesome. I hope you guys have a great day.